Hi, welcome to this review lecture on the conservation of momentum. Now, this is going to be a long lecture, so hold tight, but there's a lot of good ideas in here. So we just talked about conservation of mass. There it is in integral form. And just to review, this is the time rate of change of mass in the control volume, and this second integral represents all the flux surfaces where there's mass flux through the control volume. Here's the conservation of linear momentum. So it looks very similar to that. In fact, we just dotted this equation here with the velocity. So you see there's an extra velocity term in each one of those integrals, and the left-hand side is equal to the applied loads. Those are both the surface forces, like pressure that acts only on the surface, or the body forces, like gravity that acts over the whole body. That first term there represents the time rate of change in momentum. You can see that if you see that rho specific volume or rho small volume, that's equal to small mass. Mass times velocity is momentum. I sum up all the momentum in the control volume. So now I have the sum of momentum in the control volume. I take the derivative with respect to time. I have the time rate of change of the sum of the momentum in the control volume. How was that? All right, what about this guy right here? The second term here, I see here that this is the volume flow rate through the flux surface, rho times velocity, right? That has units of volume flow rate through an area. And then, that has a unit that has mass, right? So that's mass flux through an area times velocity. That would be momentum through the control surface. And then I sum them all up. That would be the rate of change of the mass through the control surface. This guy right here is the dot product, right? So that represents just what's fluxing through that area. That's where that vector gets realigned. All right, so we sum them all up, all of them for each control surface. It's important to recognize that this fundamentally is a scalar equation, so that means we write it once, and when we talk about mass going into control volume, we could care less from where it comes in. However, this is a vector equation, and the giveaway is that term's a vector. So you can see that there's a vector symbol that survives in each term. The dot product annihilates the vectors, but there's this vector here. So that's a vector equation, meaning we do care which way momentum fluxes, and we typically break it up into its x, y, z components. So here's the problem we looked at last time with this jet impacting a plate. Again, I would draw the control surface. I would delete what's inside, and then I would identify the flux surfaces. And then for the momentum approach, I would recognize that there is an applied load and it has x, y components, right? Or there is momentum flux from the control surface, and there's a momentum flux in the y direction and in the x direction and in the x direction here. So I could write the momentum equation as two equations, one in the x and one in the y direction. So it's kind of a trick question. It's one vector equation, but two scalar equations, right? All right, so let's go through the simplifying assumptions like we did last time. For steady, unsteady flow, if we assume that the flow is steady, that partial t term goes away. So it simplifies both for the mass and the momentum equation in the same way. And the steady form looks like this. And recall, you repeat that integral for every flux surface that there is. Open and closed, it's the same as before. We identify whether mass fluxes across the control volume at a control surface. So here there's one flux surface, and here there's two. So that means I would write one flux integral for this problem because there's one flux surface, and I have to retain my unsteady term. And in this set of equations, I don't have an unsteady term, that's gone, but I have two flux surfaces, so I write the flux integral twice, right? For the mass, and again, for the momentum, I write it twice, and I still have my sum of forces. So this is the conservation of mass. That's the conservation of momentum. Compressible, incompressible just has to do with the density, and if the density is constant or not. So if the density is constant, then we can pull that density out of the integral formulation. However, they don't divide out like they did before. So unlike conservation of mass, where the left-hand side is equal to 0, we could actually divide it out. We could pull it out of the integral and then just divide it into that 0, and you end up with the sum of volume fluxes, right? Which isn't a conserved quantity, but is for incompressible flow. All right, also associated with this viscid-inviscid assumption, just like before, we're assuming that the real boundary layer profile is replaced by the average profile. And what that does for us is it lets us then pull the velocities out of the integrals and greatly simplifies the problem. So you end up with just, in conservation of mass, just the integral of the small differential areas, which is the total area. And then here, we've pulled out the integral of the velocities and the densities, and we end up again with just the integral of the areas. So you would have, in conservation of mass, the sum of all the flux surfaces of rho VA, that's m dot, and over here you get rho VA, so that's your m dot times the average velocity again. And notice that's still a vector, and it's important when you do these problems, because remember, you have to include the directional component. So this bit's a scalar, the m dot, but yet that vector on the velocity determines the direction. All right, so if the velocity is constant, it simplifies the flux term, as we just said. And when we perform that integral from the previous slide, you end up with this expression that you might recall for conservation of mass. That's the sum of all the outs minus the sum of all the ins, and that negative sign in both cases comes from the definition or our standard that the unit normals always point outwardly normal, and so we get out minus n. If we had said they always point inwardly normal, it would just be minus out plus n, which you'll see in some textbooks, older textbooks. Here's the conservation of momentum. The left-hand side is the sum of the forces, body and surface forces. Here's our time rate of change of momentum in the control volume, and then we sum up all of the ins and outs. Boy, that should set it. That should be out, right? Sorry, that should be n right there. All right, so you see it written like this. Now, I've slipped in this little beta here. This beta is a momentum correction factor. It's often just given to you as a number, and what it is it's a correction factor for that integral, for assuming that the velocity is constant across the flux surface. That's not true for conservation of momentum because it's velocity times velocity, so it becomes nonlinear. So we put in a correction factor. We don't need the correction factor in the conservation of mass because that integral is exact. Anyway, let's do some examples. Here's one where we've got a jet hitting a plate, and we're asked to solve for the magnitude of the force required to keep the plate stationary. So let's run through it right quick. I draw a control volume like that. And so I'm eliminating all the goodness inside of the plate here, the friction along the plate of the liquid and so forth. I can ignore all of that because we're ignoring everything in the control volume. Here's our assumptions and how these assumptions will simplify our governing equations. If we assume that it's steady, away goes the unsteady terms. If I assume that it's an open system, I can see that mass is fluxing in here and here and here. So it's an open system with two flux surfaces, so I repeat this mass integral twice for the out and for one for the in, and again I've got the two momentum integrals for the flux surface out and in. And then I've also put on the applied force. I've only got one applied force. It's this F to hold the plate stationary. It's acting in the minus J direction. So notice I'm still writing this as a vector equation, right? So I have the IJs in there. If I assume plug flow or inviscid flow, then the integral, I can replace the integrals with just the algebraic form, and it's at that point that I change the sign of my n terms. Here, for the conservation of momentum, I'm just taking the y direction, so that's just the j components, that j and this j. So we're ignoring the x, that's the momentum in the x direction, so I get the y direction of momentum is just minus this j, plus this integral term, which I haven't simplified yet with regard to plug flow, but when I do, I would pull out the velocities and the density because I'm assuming that it's incompressible, and I'm left with just the integral of RD theta for a circle, and so I get pi r squared, that's the area, and so there's our flux term, and then I can just solve for the force, and I get 17.6, which looks like about that guy right there. All right, let's do another example. This really belongs with conservation of mass, but it sets up the third example problem. So let's go through it first. If water flows steadily in a pipe that's inclined with a laminar profile. Here I'm giving you the profile, so that tips you off that we're going to have to integrate. What's the average velocity? So here's the profile, and we're asking what's the average velocity in terms of Umax. So let's use the conservation of mass equation here. Here's my control volume. I'm assuming that this is steady, so away goes the unsteady term. I'm assuming that it's incompressible, so I pulled the rho out of the integral. Viscous flow in, viscous flow out. And there's more than one way to solve this problem. I'm going to do it like this. You could have just performed the integral at an infinitely small control volume, which is what's typically shown in the textbooks, and you just have m dot is equal to the integral. But really, the way that that comes about is performing the integral over a larger control volume. So you can see that really those two approaches are equivalent. So what I'm assuming is that the mass flux in is our profile, and somewhere coming out is some average profile. So I have one flux surface in and one flux surface out. I have two flux surfaces. And since the average is a flat profile, I'm not even going to write it as an integral. I'm just going to say rho VA, and that's an out, so it's a positive. And here I've got the integral form, and I'm not writing it negative as an in because the negative sign is built into that unit normal, right? So I insert the velocity profile here. This is what I was given. So as soon as you're given a velocity profile, you know you're going to have to integrate it. I insert the velocity profile. I know that the unit normal here in 1 is equal to minus I. So that goes in right there, and that's where the minus sign comes from. The differential area is r d theta, so that's where that comes from. I integrate, turn the crank on some math, and I see that the average velocity here is half of Umax. So here's Umax right there. It's the center line. So the average velocity would be halfway through. Now that's not true for all profiles, but it's true for this one, right? So if you're given any kind of profile, you can run through this analysis to determine what the average velocity is. Okay, now let's do a little bit harder problem, and that is, what's the relationship between the drag force on the pipe and the pressure velocity elevation? So this is a really canonical problem. It represents really a foundational problem in fluid mechanics. So what I'm asking you is, what's the drag force on the pipe as a result of this momentum flux down the pipe and the no-slip boundary condition? All right, so because we're being asked for force, force doesn't appear in conservation of momentum. It appears in conservation of mass. It only appears in the conservation of momentum. So I know I'm going to need this momentum equation. So there's the full-up momentum equation. Draw the control volume. I assume steady, goodbye unsteady term. Incompressible, so out comes the density. Viscous flow in, viscous flow out. That's the reality of the situation is that it's no slip in and out. So I write the profile on the in and the out. And I'm given the profile here. There's two flux surfaces. So maybe it'd be fun if you tried to write this profile, if you tried to write this equation with all of these assumptions. Why don't you pause the video for just a second and see if you can just write it out and what you get. Go ahead, try it. Seriously. All right, I hope you tried it. So you should have gotten something like that. So the left-hand side is the applied load. So I have a surface force here. That's the drag force. And don't forget the body forces. That's the gravity acting down. And I'm really going to work just in the x direction here. So there's a sign phi in there. Also, the pressure forces, that's a surface force as well. The pressure on the inlet and the outlet act. They act inwardly normal. So the left P1 is in the positive direction here, and the right P2 is in the negative direction. I have two flux surfaces, and there they are, 1 and 2. So I insert the boundary layer profile. I know that dA is r d theta. I know that the ends are the unit normals that point outwardly normal. So you should be able to see where all of that comes from. Now that's a lot of math. And we have this nonlinearity here. Basically we have velocity squared. So I have to run through all of that and Just turn the crank and I get this math here. And notice that the momentums in and out cancel. And why shouldn't they, right? The profile's not changing. So the momentum in is exactly equal to the momentum out. Therefore, algebraically, they cancel. So we're left with that the drag force F is equal to the weight and the pressure difference. And this goes way back to when we were talking about what does viscous drag do. The viscous drag manifests itself in the pressure difference, not in the momentum difference. Isn't that cool? You can see it right here. So we can divide through to get shear stress. I'll divide through by the area of the pipe, so that's 2 pi r times the length. And let's now just consider the horizontal pipe, so let's get rid of the gravity, and we can see here that the drag force as a result of the flow is a reduction in the pressure. So you can think of it either way. The pressure causes the shear stress, or that shear stress causes the pressure drop. All right, since the velocity dropped out, the viscous drag results in a pressure drop. I mean, that's foundational to fluid mechanics. So I can do a little bit more here. We can divide through by rho g d L4 to get head. And so this is the friction head that you may recall. This is the form of it. You can see that the friction head is related to the shear stress or the drag on the pipe or the pressure drop. So I end up with this really amazing relationship that relates the friction head to shear stress, to drag force, to pressure drop. That is cool. And we see that the units of any of these is indeed, in fact, head, which is a length, right? So this brings us to the Darcy friction factor. This is where we introduce it as the ratio of the shear stress to the dynamic pressure. So if I take that relationship I had on the previous page and divide it by the dynamic pressure, I get the Darcy friction factor. And we work through the math and we end up with this relationship here. So I can include this last one, the Darcy friction factor. So I think we'll stop here. But hopefully you saw this huge connection of a big scope of fluid mechanics just in this short lecture. So hope you enjoyed it.